There you are.
Thanks very much, Grant. Good morning, everybody. I had to sort of think back. The last time I gave a seminar here was in 1994, I think. So it's been 20 years. I'm glad there were signs up to show me the way to the lecture theatre because I couldn't remember where it was. When I was first thinking about giving this presentation, I thought maybe I would do a sort of a generic type talk on energy efficiency. With lots of motherhood statements and arm waving. You'll see lots of arm waving because that's the way I talk with my hands. I started digging through files and started thinking about things that I haven't thought about for a long time. So I decided that rather than do more of a generic one, that it would be more of a recount of what things have influenced my way of thinking with respect to energy efficiency and how I got to hold the views that I currently do now about energy efficiency. So without further ado, let me tell you a story. I came to the JK Centre in 1987, did my master's degree in SAG model, finished in 1989. Don McKee gave me a job on staff, and I'll talk to you a little bit about that in a minute. But at that time, and we're talking about SAG milling here, which was my thing, the conventional wisdom of the late 1980s was encapsulated by the views up there from a number of worthies, and they were that SAG mills and AG mills essentially were inefficient machines. Tim put me to work on what was then P9J, looking at comminution research. And one of our sponsors was a very bright man called Gary Johnson. Dominion Mining, and some of the old lags will remember Dominion Mining, it no longer exists, had a number of operations. They had 3 SABC circuits and 1 crushing ball mill circuit. And Gary Johnson, the chief metallurgist, a very conscientious, wanted to make sure that each one of his circuits was working as best as he could possibly do. So he did a few calculations himself, and I'm going to talk a little bit about what he means by that last phrase there, but he came to me and said, Steve, I've done all these calculations, and some of these circuits are better than Bond. Can't be right. Can you have a look at it? I want to just very quickly go through the Bond equation, and particularly operating work indices, particularly for those of you who are not comminuters, because it's key to the entire talk, what an operating work index is. This is, and I hope you've all seen this equation before, Bond's standard equation in predictive mode. So you do a laboratory work index test and you bolt that number in there. You specify a final product P80, a feed F80, and it gives you the kilowatt hours per ton of the machine stroke circuit that you are interested in. So that's in predictive mode. You don't have a plant. If you have a plant, then you know what that is. So you can flip that whole equation around, put WI onto this side of the equation, and we now call it an operating work index. And you give it the P80 of your plant and the F80 of your plant. And the WIO, the operating work index, has a number of very interesting properties. One of the benefits of it is that it removes the influence of product and feed size and just leaves you with these particular properties that we're interested in. So work indices, operating work indices, I'll be talking about a lot throughout the rest of this talk. How can this operating work index be used? Well, if the ore stays the same in your circuit, then it should reflect changes in energy efficiency. So in an existing plant or pilot testing, it's not often done pilot testing anymore. In the good old days, don't know how good they were, pilot testing was done very thoroughly, and lots of pilot tests were done. So if you look for the minimum operating work index, that was meant to indicate the best, from an energy efficient viewpoint, the best position that plant could be in. And I'll give an example. This is real data from a pilot test, and what I'm showing here is ball load because in this SAG mill, we're changing the ball load throughout the pilot test and the specific energy that we record in the pilot test. And here is this particular shape. It doesn't always follow this shape, but I wanted to use this because it has particular qualities. So one looks at that and says, well, yes, the minimum specific energy is down here with a high ball load, and the maximum specific energy is up there with only 4% balls. But now, let's have a look at the operating work index, which is now meant to tell us the most efficient way of running that mill with that ore. And interestingly, the whole curve flips the other way. And the thinking at the time was this then was the most energy efficient way of running that SAG mill with about 5% balls. And if you then wanted to design a circuit with the view I wanted the most efficient circuit, you would design it to run with 5% balls. How else can it be used? Well, if you want to compare different plants, the ore is obviously different. So you can't basically use it on its own. So you do a laboratory work index test as well. That becomes the benchmark. That's the best you can do. That's laboratory. And you make a ratio of your operating work index to your laboratory work index. And you can then compare the energy efficiency of different circuits by looking at that ratio. The higher the ratio, the worse that circuit is, because WIO, the operating work index, very much bigger than the lab. It means you're wasting energy. If the ratio is less than 1, it says you are beating bond. And that's what Gary Johnson meant. It's better than bond. It can't be, because the prevailing view then, and in many quarters still is, that is the benchmark and you cannot do any better. Back to Dominion Mining. He asked us, P9, what can we do to help? And there were two things we decided to do. First step, because we were into modelling, was explore the potential for looking at energy efficiency through modelling and simulation, rather than bond, because clearly there was something not quite right there. The other, good old JK methodology, let's go and collect some data. So they were the two things that we decided to do. The modelling. The first thing we decided to do was to adapt the breakage power model from the Anderson-Whiten crusher model. Those of you who know that model will know that particular algorithm very, very well. It works really, really well on crushers. And basically what it does, it assumes that size reduction occurs in a pendulum tester. In those days, it wasn't a drop weight tester, it was a twin pendulum tester. And you assume that breakage from the feed to the product is successively done in this laboratory device. You sum up all the energy that's required through breaking it with a pendulum, and you compare it to actually what's recorded in practice. With the crusher model, we ended up with some really, really, really good results, or Jan Anderson and Bill did, that the multiplier is about 1.25. So a crusher typically uses about 25% more energy than if you'd taken the feed and banged away in the pilot plant and crushed it all down. So we decided to adapt that model and bolt it into the SAG mill model and see what came out. Step 2, collecting data. Dominion Mining had two circuits on the same property. Haveluck, Paddy's Flat. Haveluck was a good old-fashioned multi-stage crushing, multi-stage ball mill circuit, and parked right next door on the same property, they had a brand new, state-of-the-art at the time, SABC circuit. SAG mill, ball mill with a pebble crusher. So he arranged to have a huge stockpile made from the pit, and over the course of 7 days I spent there, one front end loader went to the one plant and one went to the other, the whole week. So we knew same ore through both plants. Back to the simulation modelling. How well do we do there? Absolute rubbish. We didn't have any chance whatsoever. And the reason was, for this to work, you need to know in detail the size by size strength of rocks from feed right the way down to final product. We had to make assumptions about how that shape of that curve was configured based on a narrow slice of particles that we broke with the pendulum test. And what we found was, if we changed our assumptions about how you extrapolate, you could get any number, any answer that you cared to. Shelved it, no good. What about the survey data? And this was published back in 1991. Well, this was really interesting. Paddy's Flat is the SABC circuit, and Havelock is the crushing circuit. Same feed, slightly different products. We couldn't get the final product to be exactly the same. But here, total milling energy for the SABC circuit, 11.1 kilowatt hours per tonne, 11.9 for the crushing circuit, but it is grinding finer. And even without doing an operating work index, it's fairly clear that the overall energy of a good old-fashioned multi-stage crushing and ball mill circuit was matched by an SABC circuit. Published it, but we weren't comfortable with it because at the time, again, this was saying something that surely couldn't be. I'm going to step off this path and get onto another one, which was running in parallel at the time with another sponsor. That sponsor was called Western Mining Corporation, abbreviated WMC. BHP bought them up some years ago. They're a long time sponsor of P9. They had a pilot facility in Kalgoorlie, and they used to do a lot of pilot testing, and we did a lot of work with them at the JK Centre. Now, Western Mining's belief was that the key to optimum energy efficiency with AG and SAG mills is to close circuit them. Why? Well, here's typical data from a closed circuit SAG mill, grinding from, in this case, 77 millimetres down to 229, versus an open circuit. This is pilot data, this is Western Mining's data. Obviously, closed circuit uses up a lot more energy because it's grinding finer than an open circuit. But look at the Bond operating work index. Remember, operating work index, conventional wisdom says, equals energy efficiency. Large numbers poor, low numbers good. And here we see 51 kilowatt hours per tonne open circuit versus 28 closed circuit. Huge difference. Implications being open circuit is rubbish. Shouldn't be running that way because it is not very energy efficient. And if you simply close it, you get what they called free grinding. And it was a term used in those days. Everybody was into free grinding. So what's the consequences of all this? Well, let's look at Dominion Mining first of all. And this is a bit of history for you, those of you that weren't here at the time, and even those of you who were here at the time may not realise it. Gary Johnson, Dominion Mining, taking a look at all this, he was convinced there was nothing really in it, and he really wanted to make a step change in energy efficiency. HPGRs had just come on the scene, and so he sponsored us on a one-to-one with the first HPGR research program that we did at the JK Centre. I found a machine used at the University of Newcastle crushing coal of all things, and Gary sponsored Luis Tondo for Masters qualifying, and we did our first HPGR research program. Now that gave us some credibility, and shortly afterwards Amira put together an HPGR program and we took the lead at the JK Centre, I think based on the fact that we did have some credibility. That research, the Amira research, I can't remember how long it went for, but that funded and drove the work of Ian Stevenson and his liberation work, Mike Daniels and Luis Tondo, and the modelling work that they all did. Our recognition that we really did not know enough about breakage drove a huge amount of research into breakage. It drove the development of the drop weight tester because we wanted to look at a wider particle range. It drove the research into abrasion breakage, surface breakage. We put together several abrasion mills and it was used by George Bernini in what is, in my view, groundbreaking work. Sadly, it has largely been forgotten. It was the first and still is the very best description of abrasion breaks that I've ever seen. We also decided to go downstream to fine particles, and I built something we call the grinding table to look at fine particle breakage. Don't know what happened to that. I suspect that's gone the way of quite a few things, but that was used by Alex Yankovic in his modelling work. So that all fed into fine grinding. and there were several iterations of the fine grinding project. Once again, the JK took the lead on those projects. So that all helped again with our credibility. What were the consequences of that Western mining experience? Well, it drove their design philosophy for all of their plants. Olympic Dam started life as an ABC circuit. They upgraded and put in 2 parallel single-stage AG mill circuits. They then built Leinster Nickel, which was designed as a single-stage AG mill, Mount Keith, closed circuit SAG mill followed by ball mills, Cambalda, single-stage AG mills, and they owned a large chunk at the time of Alcoa. At Pinjarra, they had 6 parallel single-stage mills. They did an expansion at a place called Wagerup, and that's the route that they took, single-stage milling, because they believed that was the way of the future for energy efficiency. Leinster Nickel, when it powered up, was a disaster. It worked out fine in the end. One of the biggest problems there was massive slurry pooling. Alcoa, where I did my master's degree, we already knew had slurry pooling problems. So out of that, I did some lab studies initially with honours students Ian Stevenson and Sam Strohmeyer. Following that, we persuaded A&I, which was an Australian mill manufacturer, the general manager there, and I'm forever thankful for John Hadaway. We persuaded John to build and donate a pilot mill, which hopefully is still down in the pilot plant, and that was used for both Lacioretti and Sebastian Tello to do their work. Fast forward now, because in terms of energy efficiency in those days, I had my hands full and I basically forgot all about energy efficiency. Too much else going on. So fast forward to 2002. I was on my own now as a consultant. I tell you what, when you're on your own and you're designing circuits, there's a prospect that one day you're going to be bailed up in front of the justice of the peace, not justice of the peace, but the lawyers or whatever, because you're in the firing line because the plant's not worked, and it tends to focus one's attention on what one's doing, and trying to make sure that you're doing as a consultant the best you possibly can, because all you've got to do to persuade the judge is you were using world's best practice and you were doing the best you can. You don't have to be right, but you've at least got to make the case, I did my best, Governor. So I started looking for what other people were doing, and in those days and still, power-based calculations were the norm. What most people were doing was using some variation on bonds, not entirely, with something called an F-SAG factor. Lots of papers about F-SAGs. It was all to do with inefficiency, F-SAG this, F-SAG that. But there was nothing there to say, well, how'd you get an F-SAG? Because it was all, this is secret guy stuff, you know, you're not allowed to know all about that. So what I decided to do, in the good old JK training way, let's collect some data to have a look. And I scrounged together some data sets. I had 18 of them. Now I've joined the dots on these, not because I'm interested in showing you what that trend is, just so it makes it easier to look at. So we look at this is data set 1. That's the operating work index of the SAG mill, and that's the ball mill that follows it. And there's data set 2, data set 3, data set 4, and so on. What it clearly shows is that operating work indices of all these SAG mills are all much higher than the ball mills. And this difference is F-SAG. Effectively, that's F-SAG. And in this plant, it's a big F-SAG, and in this one, it's a small one. So I thought, there's something going on here. If I could just work out what the relationship was, I'd have a nice little model where I could predict F-SAG and I'd be away. So I started looking, what could I find? This graph is the single most influential graph I've ever drawn with respect to energy efficiency. Why I drew it, I've got absolutely no idea. All I know is that I was rummaging around with pilot data, because pilot data is good because it's controlled. I thought, well, I'll stick it all on a graph and I'll look for patterns as modelers do. Is there a pattern somewhere? And I happened to print it this way. Chances are it was a mistake, but for any modeler, as soon as you see that, you think, bugger, there's something going on here. This is good. There's scatter, because of course these are from different ores and from different pilot programs, but there's something going on. So what I'm graphing here to remind you, this is the product size, P80, of each of those pilot tests versus the bond operating work index. Well, maybe I've got an FSAG model here. This is really good. So sat down to think about what this was actually telling me. Now remember, operating work index equals efficiency, maybe. So is this saying to me the ore's getting easier to grind as it gets finer? No, it can't be right. Is it saying to me that mills are getting more energy efficient because the bond operating work index is getting lower as they grind finer? No, that can't be right either. Can't be. Maybe, and this is absolute heresy of the day, punishable by crucifixion, bond's operating work index is incorrect. No, can't be. So I thought, well, I'll go and see what is said by other people. And I do remember old Hukki or Hukki. This guy should get a prize for the best title of a paper ever. Proposal for a Solomonic settlement between the theories of von Rittinger, Kick and Bond. I mean, it's bloody brilliant. For those of you not too familiar with biblical references, Solomonic comes from King Solomon in the Old Testament, wise man. So it's a wise proposal for the settlement of all these various theories. And there's this very famous graph that keeps on getting repeated time and time again. And I have to say, for those students among you, be very careful about this graph, because Hukki's been very naughty with this graph, because it's actually not quite right. A couple of things to remind you. We normally put cumulative energy, like a signature plot. This is not cumulative energy. Each of these data points are instantaneous specific energy to get from the next highest size down to that particular size. Very unusual way of plotting stuff. It's not a problem, but just remember it. What the data is, and he says what each data points are. These are his data points. And he quotes them as to what he's assumed. And it makes a very, very pretty picture. Well, I decided, I've got a lot of data now, I'd go and find industrial data and parcel it out into the ranges that he's used here for what the specific energy is to go typically from 100 millimeters down to 10 and so on and so on. So this is, as far as I can determine, is the current status of how much energy for each of those is. It looks like that. Right? So it's nothing like Hukki said. So what Hukki said basically, in one respect, is wrong. The settlement, in fact, is not resolved at all. It's not important. In fact, my personal view is anybody that tries to bring it all together, like, you're wasting your bloody time. Really, it has no value whatsoever. What does have value is his idea, and it was a bloody good idea, and it's not an original idea, that having a constant, whether you're von Rittinger or Kick, maybe that's not such a good idea, and that maybe it's a variable that changes with things, and that was a really neat idea. So what I decided to do, can I find that function, that variable function that does what I want it to do? And all I simply did, and it was very, very, very simple stuff. I took each of my pilot data sets. There's one of them there that shows that bond operating work index trend that gets finer and finer and finer particle size. I looked for some equation, and I tried all sorts of different ones, that would straighten that line on the assumption that basically the operating work index should be constant with particle size, because the whole idea of the operating work index is it's taken the size distribution out of the equation. So there should be no trend at all. And that was the function. There were a number of others that probably worked equally well, but that's the one I came up with because it was simple. There is nothing fundamental about it at all. It doesn't say, and I don't want it ever to mean anything about anything. It simply is the best fit to my data. And that's as good as it gets as far as I can see. And I've already seen people say, oh, well, it doesn't do this, and is it like Kick, or is it like... Doesn't matter. Doesn't matter whatsoever. It is a pragmatic approach. That's all it is. So this is, and what has become known as, and the Global Mining Standards Group has now adopted it, the Morrell equation, the Morrell methods. There it is. Looks like Bond, and I make no apologies for that whatsoever, because I think the actual form of that equation is easy to understand. But I don't have a minus 0.5. I have this function, and that's the simple function. And it can be used just like Bond's equations. You just simply need laboratory tests to give you that, and you can turn it around to give you an operating work index. So let's revisit those graphs I showed you before, right, which is Bond operating work index space. Here's this graph that had been interpreted that this was the most efficient way of running that circuit. That just so happens, if you plot these same data, ball load against product size, that minimum energy, specific energy also coincides with the finest grind. So I think you probably know where this is going to. When you use the new equation, my equation, basically you end up with a straight line. Basically says none of those conditions is any more energy efficient than the others within the limits of our ability to measure it. There is no minimum energy efficiency at all. It's an artifact of the Bond equation. Let's go back and revisit free grinding. There's the Bond operating work index difference. It says open circuit, rubbish, closed circuit, much more energy efficient. When you use the equation that I proposed, it basically says open circuit, closed circuit, there ain't no difference, at least no significant difference at all. None of them is wasting any more energy than the other. They may be used in a slightly different way, but it's not being wasted, which was the free grinding approach. Let's go back now to my data set. Where's the FSAGs gone? Well, they're not there. They never were there. Well, they were there, but they were there because the Bond operating work index had an inherent bias in it. So, conclusion, double heresy. Not only is Bond not right, but there is no significant difference, according to this, between the energy efficiency of SAG mills and ball mills. That flow right in the face of what everybody had thought up until that point. Did anybody else agree with this? Well, there are actually quite a few papers that agree with this. I don't actually say it in so many words, but SAG 2001, Larsen et al. Wrote a very nice paper. They pilot tested their all. And Rob will know this work, because I know you work very closely with Larsen, Chris Larsen, who was very much a friend of the JK Centre. They pilot tested SAG mill, ball mill and circuit, AG mill, ball mill, AG mill with a crusher with ball mill, AG mill with pebble mill, crushing, rod mill, ball mill. Same feed, ground to the same product. And this is a quote from his paper. Within the accuracy of test results, very important proviso, very important. There is no significant difference in the total energy required for any of these alternatives. He then went on to say, because their old circuit was crushing, rod mill, ball mill, and their new circuit was a single stage SAG. Numerous sampling campaigns and power measurements have shown the retrofit comminution circuit is performing at the same net energy efficient level as the former conventional circuit when evaluated at the same final grind. No difference. So there was experimental data out there that actually confirmed that assertion that there ain't no difference. What I'm not saying is that it doesn't matter what you do with a circuit. They're all magically energy efficiency. Wrong. For those who've operated plants, you can make a plant work really in efficiency. It is dead easy. It's not so easy to make it work very energy efficient, but you can ruin it without any effort whatsoever. Good example of this is not actually running the circuit. If you have to turn down the feed rate of a SAG mill, or any grinding circuit, particularly a SAG mill circuit, let's say something's gone wrong down in the filtration plant, it's down to half power, you have to turn the throughput down. If you log, and this comes from a log of a particular plant I did some work on, I've got tons per hour here along the x-axis and the SAG kilowatt hours per tonne here on the y-axis. You can see when we're going flat chat, the plant's flat out, specific energy is 4.5 kilowatt hours per tonne. We have to turn the feed down now because there's a problem downstream, and as you ramp down the feed, the specific energy goes up and up and up and up. Bigger the ball charge, the worse this equation gets. By the time you're down here, that mill is rattling like you would not believe, because what you're doing down here is grinding steel balls, because the mill basically empties out and you just simply, and you are wasting energy, no two ways about it. So you definitely can make a circuit run at energy and efficiency. But once optimized, within our ability to measure, don't ever forget that, because our ability to measure is not that crash hot. And statistically, you can show quite clearly that you're lucky to get within plus or minus 10%. Lucky, particularly with modern day circuits. So within that envelope, just remember, I've got some really emotional responses to me saying this about bonds. Sometimes quite personal, I have to say. But typically, it's just, no, it's rubbish, it can't be right. Bond can't be wrong. We've been using it successfully for years. Particular quote from Rob McIver, who is the world's foremost proponent of bonds, and he's the one that generally gets very emotional with me if I say anything against bond. This is a quote of his. Bond index is easy. Okay, it's easy. It has decades of data to support its value and has been used extensively to benchmark a given circuit's energy efficiency. And we're going to look at that in a little bit more detail. Before I do that, I want to actually give you a quote of Bond's. It's something I've never seen before. This is Bond's quote about Bond's technique. Many, and he talks about his equations, are empirical. I've got no problems with empiricism until you start to extrapolate. And then if you're not careful, all the wheels fall off. And Bond empiricized back in, and he started his work in the 30s with his little data set down there. So just remember that. But it's this second thing that has me a little bit uncomfortable. With numerous constants being derived from experience. So what I read into that is there's lots of guesswork in those equations, which makes me even more, not so much upset, but concerned, the slavish adherence that most people have to, if Bond says it, it must be correct because Bond said it was correct. Published data then. So let's have a look at all this benchmarking over decades. This comes from Flavel and Rimmer. Flavel and Rimmer worked for Alice Chalmers. Bond worked for Alice Chalmers while he developed all his techniques. Flavel and Rimmer worked for Alice Chalmers. They came after Bond. Flavel and Rimmer rubbished the Bond crushing work index test because they went out and they collected data and they said, this is not a good crushing work index test because here's our data. Observed operating work index versus laboratory work index. And in fact, Alice Chalmers went away from the crushing work index. They developed their own twin pendulum crushing device. So that's as much crushing data as I can find in benchmarking data. It's not good. It's very poor indeed. Bond, of course, and if Bond tried to publish a paper today, it would be refused because he didn't give any data whatsoever. He just simply said, trust me. Fine, where have you heard that before? This is Rowland's data, some of it's Rowland's data. That's these brown points. Rowland came after Bond and very much a disciple of Bond's. These are his ball mill data and these are his rod mill data. These blue points are from a guy called Blaskett. And Blaskett was in the CSIRO in the early 60s. And Blaskett published a paper where he surveyed a lot of Australian ball mill circuits. He published this paper, did a really, really thorough job of examining how well the Bond test worked. And these are his crushing data sets. This one in particular was very, very bad. We don't have the time to talk about this. There's a very good reason why this was very, very, very poor. The thing to remember about the ball mill data, typically here, is they tend to be on this side of the curve. Meaning that if you use them to predict what the specific energy would be, you would tend to predict a higher specific energy than in the plant. And as a designer, you would tend to put a slightly bigger ball mill than was absolutely necessary. So you could be almost guaranteed it would be successful. So you have to think about, yes, Bond has been successful. Yes, it has. Because if you always make the mill bigger than it needs to be, of course you're going to be successful. You've never been taken to court for your plant failing to work. Doesn't necessarily mean from a scientific viewpoint it's accurate, but from a designer's viewpoint it works. The rod mill stuff is really interesting because it's on the other side of the line. Rowland's comment about this is telling. He says this has got nothing to do with the Bond equation being wrong. It must be these rod mill circuits weren't being run efficiently. Okay, maybe. I don't actually have very many rod mill data sets. I've got 3. Guess what? It's bang on Rowland's data. So to be fair, there is actually a trend there, and I suspect if you were that way inclined, you could bolt on a correction factor to the Bond-Rodmill equation to make it work better. But as it stands, there is no evidence there that says that works very well either. The other thing that Roland said, well, it doesn't matter that you've now undersized the rod mill, because rod mills are in open circuit with ball mills. Ball mill does all the work, and ball mills always work really well. So actually, who cares? Because you don't really care about it. And as it transpires, because you're oversizing the ball mill, you undersize the rod mill, basically it all evens out and the circuit works. So again, from a success viewpoint, yes, of course you'd make that conclusion over 20 years. It always works. These are my data from ball mills following SAG mill circuits. I've done my very best to make this look as good as I possibly can. To do these calculations, you have to give the ball mill what's called the transfer size. So I've given it the measured transfer size. In predictive mode, you haven't got a bloody clue what the transfer size is. You've got to guess it. So it actually would be worse than this in real life. But the trend is also, there's a trend there, don't get me wrong. But again, the trend is you're tending to make the ball mills bigger than necessary, so the plant will work. So again, it supports that. It's always worked. So don't have a problem with that. As a designer, I don't have a problem with that at all. The interesting thing, let's go back to this minus 0.5. And that's the thing that I'm really saying is not right. For those of you who have ever done a lab work index test, that's the equation you use. You do your lab test, you put in the net grams per revolution there. That's the closing screen size. The bond test is typically done with about a 2mm feed, Baldwin, and the product size of your plant. That's how you should do it. So you do your lab test. That WI gets bolted into there, because this is the predictive equation. You give it the product size of your plant, which is the same as that. And in a lot of cases, and for SAG mills, an assumption of about 2mm feed size is actually not a bad one. The fact is, if you plug that into that, this cancels out. Closing screen size is directly related to the P80. It's a factor of about 1.4. So when you do all of that, the actual equation you're using with bond to size a mill doesn't have anything to the minus 0.5 at all. It has something to the minus 2.3. Actually, that's not true, because the net grams per revolution is also a function of P80. You end up with a very complex function of P80, and it is not 0.5. So yes, bond may have worked in design, but it didn't work because of minus 0.5. It worked for all sorts of other rooms, but not to the power of minus 0.5. The total tumbling mill circuit, ag, SAG mill, ball mill all together as a black box, you know that energy. You can work out the ag mill part of it, and the ball mill basically is what's left over. So it's by subtraction. And that approach has now been adopted by OMC, by Senko, and a number of other authors. And it basically recognizes the fact that in ag, SAG, ball mill circuits, that transfer size distribution is unusable in the conventional power-based equation. You must not use it. Okay, my data. This is the crushing circuit, observed versus predicted. These are the HPGR circuits. The blue ones are lab pilot. The purple ones are full scale. There's not a lot of full scale circuits around. I've managed to benchmark with at least 5. These are total tumbling mill circuits. Now, I should point out here, in those equations, there are no FSAGs or assumptions about energy efficiency. The underlying assumption is there is no difference in the energy efficiency associated with any tumbling mill circuit at all. So lumped in there, and you can see here we've got ball mills in HPGR circuits, ball and rod mills, ball mills in crushing circuits, and all the different sorts of SAG mill circuits. And yes, there are scatter, and the error standard deviation is 6.6%. So 2 standard deviations, you're looking at 13, 14%. So within that error band, there is no indication from these data. Again, this is a derived conclusion. Having treated them as being the same from an energy efficiency, the conclusions are that yes, they are the same from an energy efficiency viewpoint within that error bound of about 12%, 13%. I've done an error analysis of this, and I can't find any trends associated with different types of circuit. It appears at this stage to be random error in there rather than any form of systematic error. There are the ag-SAG circuits. and they're the ball mill circuit. So I've collected a fair amount of data that suggests that it's not bad. It's damn sight better than Bond, I say that. So, conclusions. The first is that Bond's minus 0.5 is not valid over the full range of circuits. It may well be valid over a short run, but if you're looking at using it over a wide range, it doesn't work. So if you're using Bond operating work indices to evaluate energy efficiency, you are in grave danger of making some serious conclusions, wrong conclusions. As I showed earlier on, Western Mining, yes, they ended up with single stage mills, nothing wrong with that, but they ended up with them for the wrong reason. They thought they were marvellously power efficient, they weren't. It was a Bond operating work index conclusion. Bond's methodology for sizing ball mills is really not that accurate, but yet actually it does work if your criterion is, I've not been taken to court for building a plant that doesn't work. That's not a bad criterion as a designer, believe me, it's not. As a scientist or an engineer, it's not good enough. It simply is not good enough to say it works, therefore I'm going to stick with it. There are better alternatives. Specifically, however, Bond for crushing and rod mills has serious problems. I've paraphrased, because this is the most important one for me, I've paraphrased Chris Larsen's conclusion, which is the last of my conclusions. Within the accuracy of our ability to measure such things, there is actually, I cannot find any concrete evidence overall. Yes, there might be pockets where somebody will say, oh, this is better than this. Overall, I cannot find any difference in the energy efficiency between different well-run tumbling mill circuits. Rod mills, ball mills, ag mills, SAG mills. No others, nothing else. I'm not saying anything about anything else. To conclude, I want to leave you with two thoughts. The first one is less important. The second one is the most important. First one, if it looks too good to be true, then it probably is. Beware of claims of there's huge amounts of energy to be found out there that's being wasted. My experience is no, sorry. And the reason is, point two, because there's no such thing as a free lunch. Somewhere or other, my experience has been that energy is used. You may not know it at the time and you think you're saving it here. But when you take a much more holistic view, and I'm talking about really big holistic views, when you're looking at carbon footprint and environment, there's a very good chance that when you think you've just saved energy, you haven't. Doesn't mean to say there aren't opportunities out there, but it's just a word of warning from what has become an older and far more cynical man than when I first started in this business. And what I haven't put here, but for the students among you, I would strongly encourage you to challenge everything, including all the stuff I've just given you. Don't just sort of lie down and accept the greybeard saying, this is the way things are, because there's a bloody good chance that they're not. Thank you.